Hello, Western. I'd like to talk about another wave phenomenon. This one is unrelated to the superposition principle, and it's called the Doppler effect. The Doppler effect is the change in the frequency of a wave caused by a moving source or a moving observer. And this can be observed if you stand next to a train as it passes. And if you've ever done this before, you notice that the sound of the horn on the train has a different pitch when the train is moving towards you than it has when it's moving away from you. And this is because of the Doppler effect. Now we can understand why this occurs if we think about a moving source. So here I have the circle at the center, which is a source, and then I have this curve right here that's supposed to represent the crest of a wave that's produced by the source. So at some time later, this crest is going to move forward, and the source is going to produce yet another wave behind it. And the distance between these two crests will be equal to the wavelength. However, if the source is moving, it still produces this crest, and this crest is still going to move forward, and it'll be at the same place. However, because the source has moved, the second wave crest that's formed is going to be closer to the original wave, and as a result, the wavelength becomes shorter. Now, even though the frequency is what's responsible for the pitch of a sound, it's easier to calculate the effect of a moving source by first calculating what the change in the wavelength will be, and then using the relationship that the velocity of the wave is equal to frequency times wavelength to find the new frequency. So, as we can see here, the new wavelength of the wave when the source is moving is going to be equal to the speed that the wave was moving at minus the speed of the source times the period of the source, which can also be written as this, c minus vs divided by frequency. Now you'll notice here that I'm using c for the speed of a wave, and I'm doing this because we now have three different speeds that we're going to be talking about. There's the speed of the wave, the speed of the source, and we'll also talk later about the speed of the observer. So, like I said before, the frequency is what really determines the sound that you hear. So, we would now like to solve for the frequency. So, the frequency that we hear is equal to c divided by the new wavelength. And plugging in the formula that I had on the previous slide, we get that this is equal to the initial frequency, or the frequency you hear at rest, times c divided by c minus the speed of the source. And dividing every term in here by c, I can write this like this. Now notice that this formula always gives us a value that is greater than the initial frequency, because I'm taking 1, subtracting something from it. So the number in the denominator here is less than 1. When I have a number in the denominator that's less than 1 like this, I'm going to wind up with something that's going to be bigger. So in general, what we see is that when the source is moving towards the observer, the frequency increases, and we have this formula. However, when the source is moving away from the observer, the sign of the velocity switches, and the frequency is going to decrease because this denominator will be greater than 1. So this is what happens when the source is moving. What happens if the observer is moving? Well, when the observer moves, it doesn't have any effect on the wavelength of the wave. However, the observer sees the wave moving at a different speed. And of course, we can just use Galilean relativity to find out that effect. Again, of course, we're assuming that this wave is non-relativistic, so these are like sound waves. This won't work for light. So, plugging this into the other formula we have for the speed of the wave, we can solve for the frequency. So the frequency is equal to the speed of the wave divided by its wavelength. And the speed of the wave is equal to the speed of the wave minus the velocity of the observer. Now, finally, I can plug in the fact that the initial wavelength would be equal to the speed of the wave divided by its frequency. Plugging this in, I have that my frequency that I observe is equal to the initial frequency times c minus v naught over c. Now notice that if the observer is moving away from the source, then we have this formula right here, and that means that the frequency is going to decrease. However, if the observer is moving towards the source, then we'll have a different formula I have here on this next slide, where we have this plus sign, so the frequency appears to increase. And so that's pretty much the Doppler effect. Now, you don't need to know any of these formulas that I gave on the previous slides for the AP exam. The big picture that you need to remember, though, is that when the source or the observer are moving towards each other, the frequency tends to increase. And when the source or the observer are moving away from each other, the frequency tends to decrease.